So far we discussed SVD, and we will conclude our discussion of singular value decomposition by looking at an example of its usage and then talk a bit more broadly about the method. So here is the idea. Let's think about the following problem. Imagine we want to identify all the users who like our Matrix movie. So the idea is we have this matrix now of values of users to movies, and now we would like to identify all the users who like the movie Matrix. And what we would like to learn from this task, in a sense, is that given that we saw that there are people who like sci-fi movies, so maybe we would like to kind of find a person who didn't even see the movie Matrix yet, but we may want to be able to say, yes, but given that they like these other sci-fi movies, they may also like the movie Matrix. And the question is, how can we do this using SVD? The answer to this question is that basically we want to map our query point into the concept space. We are given our data, users to movies Matrix A, right? We do the SVD of it. So here's the SVD. And what we want to do now is we are given our query point. Our query point Q is simply, we say, let's find all the users that like the movie Matrix. So let's create, in some sense, this query user, this artificial user that likes the movie Matrix. And the idea is we want to find other users who are close to this given user in the concept space. So what we will do is we have our movies space, we have our data point Q here, our query point, and we want to project it into our concept space. The way we do this is that basically we simply do the inner product of our query point with each concept vector in vector V, because vector V is movies to concepts vector, right? So if we go do this, why is taking the inner product a good idea? Because, for example, Q times the first singular vector will simply take our position of the point Q and will tell us its location along the axis of the first singular vector. The second singular vector is orthogonal to the first one, so here it is, the V2, and when I multiply Q times V2, we will basically now get the projection of that data point and its position on the second singular vector. So that's basically what will happen. So if we do our projection, so we take our vector Q, multiply it with matrix V, we do the thing, and here is what we obtain. So we obtain that this, for example, this particular user, now we are in this concept space, in this two-dimensional concept space, where the first column of V is sci-fi, and the second column of V was romance. And now as we do the inner product, we basically see that our query point, in some sense, corresponds heavily to the sci-fi concept and has a very low coordinate value along the romance concept. So this is now how we took the query and kind of mapped it into the concept space. So now, for example, imagine I have some user D that we don't know what they think, or they haven't told us anything about what they think about the movie Matrix, but they tell us they really like movies Alien and Serenity. So now if I take this user, again, multiply them by our vector V, and basically move them to the concept space, here are the coordinates or the position of that user in the concept space. So what is a good thing that happened? So for example, if I now compare the positions of the original user and the query in the original space and their locations in the concept space, I find the following. So the similarity between Q and D in our original space is 0, right? In a sense that for Alien and Serenity, our query doesn't want them. For our movie Matrix, the user didn't tell us anything, so there is no similarity between these two vectors. But if I go back to my concept space, here I see that both of these data points, or both of these users, Q and D, they actually share high values on the sci-fi concept, and they share low values on the romance concept. So in some sense, I'm able to identify, or I'm able to put together that Q and D are actually close together in our space, even though in the raw data representation, they don't share any coordinates together. So in some sense, even though Q and D have 0 ratings in common, we are able to identify that they are similar. because SVD was able to identify that kind of people who liked Alien and Serenity also liked the Matrix movie. So this basically is how we can make use of singular value decomposition. What I want to do now very briefly is to relate singular value decomposition to another type of decomposition of a matrix that is called eigenvalue decomposition. So first I will tell you what is the relationship between singular value decomposition and eigen decomposition, and then we will conclude. So what we know so far is that SVD is given a matrix. We represent it as a product of three matrices, U, sigma, and V transpose. What is eigenvalue decomposition? Eigenvalue decomposition is kind of more constrained. It says, given some matrix A, I want to represent it as a matrix X times the matrix capital lambda times X transpose again. So here I only have kind of product of two matrices, if you like, lambda and X. So for eigen decomposition to even exist, what we have to do is first A has to be symmetric, which means that the values above the diagonal have to be the same as values below the diagonal. While, for example, in SVD, we did not have this constraint. And then both in SVD and eigenvalue decomposition, all the matrices are column orthonormal, which means that columns are orthogonal to each other and have unit length. And in both cases, U, sigma, and lambda are diagonal matrices. So now the question is, what is the correspondence between singular value decomposition and eigen decomposition? So let's consider this simple case. Let's consider what is A times A transpose. So we know that we can take the matrix A and perform singular value decomposition of it. So let's do that. So what is A times A transpose is the singular value decomposition of A times the singular value decomposition of A transpose, which is the same as singular value decomposition of A and then transposing that. So now let's start thinking, what do we get next? Right, what we get next is that because the multiplication is commutative, we can kind of reorder the terms, right? So for example, we can take the original expression and now just reorder the terms or the order of multiplication. What we notice now is that we get a multiplication of V transpose times V. And given that our matrices are orthonormal, this means that a matrix multiplied with itself gives us an identity matrix. An identity matrix is simply a matrix that has zeros off the diagonal and it has values of 1 on the diagonal. So what this means is that it's basically an identity matrix, right? So what this means is that we can take A transpose and transform it down. If we take its SVD and see what happens, it turns out to become U times sigma, sigma transpose, U transpose. Okay? Similarly, the same thing happens, or a similar thing happens if I ask what is the singular value decomposition of matrix A times A transpose. I do the same trick as before, and here now I obtain that this equals V times sigma transpose times V transpose. One thing that I have to remember is that sigma is a diagonal matrix. So in some sense, sigma times sigma transpose is nothing else than another diagonal matrix that has the squares of the values on the diagonal, right? So what do we learn from this is the following. So if I take the A times A transpose, which is a symmetric matrix, I do a singular value decomposition of it, what I end up with is an expression like this, which basically means that in this case, U is a set of I can think of U as a set of eigenvectors, right? So as a part of the eigen decomposition, and I can think of sigma times sigma transpose as a set of eigenvalues. So what this basically means is that if I have a matrix, I can do singular value decomposition of it, and from singular value decomposition of it, I can do the eigenvalue decomposition, where the relationship between eigenvalues and the singular values is that singular values squared are the eigenvalues of the corresponding matrix. So that's the connection between the eigenvalue and the singular value decomposition. So to finish talking about singular value decomposition, here is it gives us the optimal low rank approximation, right, in terms of the Frobenius norm. So it means that if I allow myself to take my data and represent it using a small number of dimensions, then SVD will be able to identify the best possible number of dimensions that basically give us the best possible projection of the data into some small dimensional space in such a way that if we go from this small dimensional space back to the original high dimensional space, the sum of the squares of the reconstructions errors will be as small as possible. So that's great. What is problematic with SVD are two things. First one is the interpretation problem. What this means that the singular vectors specify some linear combination of input columns or rows, which means that many times singular vectors are very hard to interpret. When I say singular vectors are hard to interpret in our cases of movies to users matrix, I was able to interpret the first singular vector to correspond to the sci-fi movies and the second one to the romance movies. Many times that is hard to do. And the second big drawback of singular value decomposition is what is called lack of sparsity. What this means is that the input matrix A is often very sparse, which means it is full of zeros and only has a few non-zero elements in it. But when we do singular value decomposition, the matrices U and V transpose, they will be dense. What I mean by that is basically all the values in this matrix will be non-zero. So many times, even though U and V have a very small number of columns or rows, so in some sense, in terms of the row column or row size, they are much smaller than the matrix A. In terms of the data size, may be bigger because A has very few non-zero elements or values, and then matrices U and V have a large number of non-zero elements. So what we will do next is we will look at the method that is much easier to compute, much faster to compute than the singular value decomposition, and also maintains the sparsity of rows and columns of U and V. And this is what we are going to look at next.